Welcome to the pre-recording of lecture 28 of an introductory course in supercomputing. So today we consider synchronized computations and in particular barriers. We will see implementations of barriers, introducing a new command in message passing, the send-receive. Data parallelism is one way of thinking in parallel, or thinking for the algorithms designed for parallel algorithms. We will see one classical algorithm, the prefix sum algorithm. This will be defined in with message passing. The shared memory parallel computation will be left as an exercise. In a later lecture, I will explain the GPU accelerated version. At the end, I will state Brent's theorem, which is a simplified theoretical model to reason on parallel performance. Okay, so let's go ahead. So we have actually already encountered barriers, but actually not really stated a very formal definition. So that is done with this slide. Also, this makes this lecture more self-contained. So in a synchronized computation, the processors have to go through a number of stages, number of steps, and they have to wait for everybody else for this step to be completed. So a synchronization barrier will actually guarantee that no processor continues to the next stage until all processors have finished the current stage. So it's used in synchronization, sometimes very useful for printing purposes, to check what every processor is doing. Often also really necessary to guarantee the correctness of an algorithm, of a parallel algorithm. So here are the examples. So in this course we do distributed memory parallel computing, shared memory parallel computing, and accelerated computing. Here are three examples. In message passing we have used already the MPI barrier. OpenMP has the construct pragma OMP barrier. And in CUDA, we can synchronize all the threads within a block by the command sync threads. That's a command that we have encountered as well. So in the definition, a processor means either a process, a thread, or a task. So the purpose of this lecture is to look into the algorithms that go into implementing a barrier. The first implementation is a linear barrier. When we talk about an implementation, we also have to define it more carefully. So a barrier, any barrier, will have two phases. So there is the arrival of the trapping phase, and then there is the departure or the release phase. In the manager-worker paradigm, we can implement this as follows by counting whether all workers have sent a message to the manager. So there is the first loop. The manager receives p-1 messages, and the manager will be blocked in this loop until every worker has sent to the manager. So there are p processors, there are p-1 workers, so the code for the worker is what the worker does. So there is another parallel loop that is going on. So at the second column in the table, every worker sends to the manager. So there are p-1 sends and p-1 receives. So the worker and the manager are synchronized. So for every matching send, there should be a matching receive. For every receive, there should be a send. So the worker and manager will be waiting on each other. Manager will wait for the worker to send a message. A worker will have to wait for the manager to have received the message. So the second loop can only start, so the second loop is then the release phase or the departure phase. The second loop can only start after the first loop has been terminated. So in between these two loops is then the code that everybody will execute. That is the synchronization. So it is a linear barrier. It takes as many steps proportional to the number of processors. Here is the picture which illustrates the algorithm. So we have 8 processors, and the arrows symbolize the send and the receive steps. So there are 7 arrows in the arrival phase or the trapping phase, and there are 7 arrows going out in the departure phase or the release phase. So all in all, this takes 14 steps for 8 processors. Linear. It's an effective algorithm, and it will be working quite fine for a limited number of processors, but if you are working with, say, more than 1000 processors, you can do this a lot faster in a cost that is a logarithmic in the number. So 1024 can be reduced to about 10 if you work with a large number of processors. So here is then a tree barrier. So I illustrate the idea with a picture. You can see that already for 8 processors there is already speed up. So there are 3 steps in the arrival or trapping phase. There are 3 steps in the departure and release phase. So in some sense, 3 times 2 is 6. It's actually not really that great. You could say it's still linear in the number of processors. It is not. But compared to the linear barrier, it's already a speed up, 14 over 6. So how does this now work? Well, it's very similar to the fan-in gathering of results and the fan-out broadcast that we have encountered earlier. So the processors are in a first stage sending to their nearest neighbor, either to the neighbor with the previous processing number or to the neighbor of the next processing number. And then the gap between the identification numbers in the sends and receives increases with every step. So at the first step, the gap is 1, then it becomes 2, then it becomes 4. So that's one way to define the algorithm. So this is done in this slide here. The definition of the algorithm, which here for simplistic reasons assumes that we have a number of processors that is a power of 2. So we have then as many stages as the 2 logarithm of the number of processors. So this is a recalling of the fan-in gather, which we now call the trapping phase of the barrier, and the fan-out broadcast or the fan-out scattering is the release phase. So there is the outer loop that counts the number of stages. There is the inner loop where the gap between the send and receiver identification number widens in each step. So in the first step, it is, if you look, I'm looking now at the release phase. So the I is actually I0, so then node J sends to node J plus 1. In the next step, when I equals 1, then the node J sends to the node J plus 2, then to node J plus 4. And there is the send and the receive. In these statements are symmetric, so you swap the identification number of the sender with that of the receiver. So the control here is the gap between the sender and the receiver identification number. Now it is then obvious that the tree barrier needs 2 times a logarithmic number of stages, 2 log of the number of processors. We can also count the total number of messages, which is linear still in the number of processors. So we care typically about the elapsed time. So if you have 1024 processors, then this will work in 20 stages instead of more than 1000 stages. So quite a considerable speed up if you have 1024 processors. We can still do better, and that's actually the next step. And in some sense, this tree barrier follows from what we know already from the fan-in and the fan-out algorithms. Now there is a better idea, and this is an algorithm that you already know. Think about 2 people who want to synchronize. All it takes is just 1 phone call. So that's the idea of the butterfly barrier. So you could also call it Ready Freddy. So here you see the step of 2 people who synchronize that just send and receive a message at the same time. So we can synchronize in 1 step between 2. So that's the base case in this recursive thinking. We synchronize all the pairs of processors, and then the pairs are synchronizing among themselves. So if you want to synchronize 2 pairs, then it suffices that one of these 2 pairs synchronizes with the other corresponding processor in the other pair. And this can happen then also, the idea is then generalized also for 8 processors. And you can see where the term butterfly comes in, because we have this crossing of the send and receive messages. The punchline is that we are done here in 3 phases, in 3 steps. So now clearly we are doing this in the number of steps that is 2 log of the total number of processors. If you have 1024 processors, then this is now done in exactly 10 steps. So twice as fast as with the tree barrier. 1 million processors, and you do this in 20 steps. So this is why logarithmic time is still considered quasi-linear. P log P would be quasi-linear. It's actually quasi-constant here. All right, the algorithm for the butterfly barrier is best understood if you have the picture in mind. So on this slide here, I have the picture with the labeling of the stages. Again, we assume logarithmic a number of processors that is a power of 2. What is important here is the gap between, or the shift, if you like, the gap between the sender and the receiver identification number. So this is computed with this S, which starts from 0, and then we have the complicated index computations for sending and receiving. So we can verify this for the formulas. So once you know the identification number of the sender versus the receiver, you also know it for the receiver versus the sender. So there is a symmetry in these two statements. So there is the gap, and there is also the modulo computation. So it can also be seen as a recursive algorithm. In the first step, you actually only consider 2 pairs. You have as many total groups as you have pairs. In the next step, you consider all pairs of couples, and then you have the last step here on the picture where you have all processors. So you can also see this as a recursive algorithm. Okay, so this is the algorithm in a picture, and generalized in pseudocode. The best descriptions of algorithms are always in code, so I will spend some time in explaining an MPI implementation. And with this, I'm introducing a very useful MPI construction. So the algorithm worked with 1 send and 1 receive. We can do this in one statement, a send-receive statement. So the send and receive is now rewritten in the send-receive statement. So we actually, the total number of statements is now reduced by 2. So shorter code is often also more efficient code. All right, so what is the syntax of the send-receive as defined by the message passing interface? Here using a C syntax, where we work with an address, beginning address of the send buffer and receive buffer, the number of elements, the type of each element, the destination, and the source. Okay, let's put this into practice. I defined one very simple send and receive between 2 processors. They send each a character. So how does this work? Well, we have the standard initialization. So every node sends to every other node. So we have the process ID, and we compute the destination for the other node. When the implementation of the butterfly barrier happens, we work with the shifts. We do the plus and then the modulo. So here the modulo 2 is the number of processors that we consider that are doing the send and receive with respect to each other. So you could also see this as a swap. So there are programming languages that can do a swap, such as Python, have the tuple assignments. You can do the swap in one statement. You can also actually see the send and the receive. So 2 send and receives that are happening now in one single statement. So every node has a send buffer and has a receive buffer. We will just send one character, so we pass the address, but it would be just as fine if you would pass strings, strings then of the same length, or every processor would need to know in advance how many characters would be sent through in every string. So processor I sends to processor J, processor I receives from processor J. So this program is executed by two processes, and there is the symmetry between the I and the J. So in a way, this lecture is self-contained. If this is still new for the parallel execution in a message passing context, so every process executes the same code, the same program. And this is C, by the way. The exercise is to do this with MPI4Pi. MPI4Pi has the send receive, actually two send receives, one with a capital letter, one with a lowercase. The capital one with the capital S corresponds to what we have seen in C. There you have to provide basically a NumPy array. So in a way, MPI4Pi follows very much the standard way of working with array processing. Just like in Julia, arrays and matrices are the main data type with scientific computing. The MPI.jl is still under development. I did a check with the version 1.8.5 that I had of Julia in the MPI Julia, and the binding did not yet exist. So if you are going to implement a butterfly barrier, then you should do this in Julia with explicit sends and receives. Okay, so that's the main exercise for this part. Implement the butterfly barrier with either C, the send and receive, implement it with the MPI4Pi, or with the Julia code. And then also, of course, the OpenMP implementation. Okay, so let's look into data parallel algorithm and look into a very classical algorithm, the prefix sum algorithm. So data parallel algorithms are in some sense the dominant model when we talk about GPU acceleration. So it is an example of the single instruction on multiple data. It's that model that actually scales very well on GPUs, where you have a massively number of cores and you need to schedule several 10,000 of threads. So it's a model, single instruction, multiple data, that lends itself very well to scalability, to a massive number of parallel computations. It's a model that was historically developed for single instructions, multiple data computers, which we now know mostly from GPU accelerators. We will illustrate this with the prefix sum and again with message passing. There will be a later lecture on how to do this with CUDA. The motivating computational problem is integration, where every process actually is responsible for executing a large number of function evaluations. And the prefix sum will do the synchronization and also the reduction. So this also fits within the category of reduction algorithms. Here is the algorithm illustrated with a picture. If we have to sum a number of elements with 8 processors, then this can be done in 8 stages. So we have encountered earlier the tree sum, but what we have now is synchronized computation, where in the first stage half of the processors are busy, and they are all busy, but there is a sending and the receiving of the data. So actually I misspoke, not half of the processors are busy, all processors are busy, and you can see that the sum is computed by computing partial sums. In the end, we will be interested only in the complete sum, but this is actually an algorithm that computes a lot more. It computes all the subsums. If you are interested in, say, convergence acceleration, you are summing the terms in a series, then this algorithm, if you have the parallelism for it, you will actually have that every processor has the whole sequence of numbers. So you are replacing the initial array by the array of all subsums. And with P processors, this can be done in a logarithmic number, again a 2-log number, 2-log of the number of processors. So this is called the prefix sum algorithm. Here is how this is defined. So we have the processors that execute these commands. So there is the initialization, there is the communication, and the computation. So the receiver will always do one addition. So we have in total to execute n-1 sums, or p-1. So here we consider the number of elements to be the number of processors. If the number of elements is a lot larger than the number of processors, of course, that will always be the case, then in the initialization, the processors will compute subsums. So this will be chunked. And you can see this prefix sum algorithm, then a form of gathering and also a form of synchronization. Okay, so the reasoning of correctness in this algorithm is again looking for the main controller. So perhaps it could be more convenient to think recursively, but that then works from a top down. And the computations are actually happening when you get to the base cases. In the base cases of this recursion, in the divide and conquer, in the base case you actually only have 2 elements, and then it is the processor that sends to the other processor. As you unwind, the gap actually doubles in each step. That also, you can only do the doubling until you reach the total number of processors. So the speed up is the total number of processors divided by the logarithm of the number of processors. So there is a communication overhead. There is one send and receive in every step. We are following something that is quite similar to the butterfly step. So this is a tree-based algorithm, but there is a lot more communication messages that are sent through, but the total number of steps is logarithmic. Okay, so let's consider an MPI implementation which completes the definition then of the program. Here the program is not in complete generality. It is done for 8 processors. It runs then in 3 stages. So there are numbers. The numbers that are being sent are summed, are the first 8 natural numbers. So we start in our identification number starting from 0. So the ith processor holds the I plus 1 number. So then there is this shift. So we have the send and receive that will then be executed. So we have one send and one receive. So the processor, it depends. So there are 3 stages here. So every one sends except the last S1s. Everyone receives except the first S1s. So there is this shift, and with the send and receive, the matching send and receive, you can count at least that there are as many sends as there are receives. There is the symmetry, and there is also the buffering. So we are sending one integer, but we are passing one integer. There is the explicit barrier that is being done here to synchronize the computations. And this is here for the main purposes of the print statements. We don't want that the print statements are kind of garbled. So there is the printing that happens after the barrier. In every step, so the last processor will have the final sum. But for correctness, we could also have printed out all the subsums. So, and that sum is stored in the number NB. Okay, so here is how the code now runs. So there are 3 steps. In the first step, everybody is actually sending and receiving, sending to the next and sending and receiving from the previous. And probably I've said this already wrong. So everybody is sending except the last node. Everybody is receiving except the first node. In step 2, there is this shift that you see. So there is also, I should probably have said this before step 2, there is the step 1 where there is the difference between the even indexed nodes and the odd indexed nodes, the ones that add after the receiving. So the odd nodes, actually not the odd nodes, I'm sorry, all the receiving nodes. So 1, 2, 3, 4, 5, 6, 7. It's confusing that they are printing in the wrong order, which illustrates the parallel nature of the execution. So even if there is an MPI barrier, they do not actually print in order. But you see that every node, except the first one, every node actually does an addition. In the second step, every one does an addition except the first 2, nodes 0 and 1. They just report the number that they have. But then all other nodes are doing an addition. So the values are increasing. So in the last and third step, you see the values that every node has. And then the last step is when the first 4 nodes are sending and the last 4 nodes they are receiving and adding. And we see all the partial sums here. So in that sense, this explains why at the very last step only the total sum was printed out. We can read off what the values are that are stored in every node. So this is the MPI version in C of the prefix sum. Okay, I will end with a model that is the parallel random access machine. It's a idealized construct for thinking about the performance of parallel shared memory uh, algorithms. So it assumes that every processor can access any item in memory instantly. So there is no memory hierarchy that needs to be taken into account. And that's already one important simplification. The other simplification is that any operation takes 1 unit time. We've seen with pipelining also that this is a very simplified model, but it allows to derive the kind of a theoretical speed up that can be obtained. So you have every processor can perform any arithmetical operation in unit time, and the computer has also enough processors to do this. So then we can compute the speed up. So with P processors, if then the time with P processors is bounded by T, which is the total time that the processors that the parallel computer can do to execute the computation. And then we have the total number of operations divided by P. So this is the statement of Brent's theorem that we can now apply to justify also the speed up. So for the parallel execution. So if you have so what's now the use of this theoretical analysis? Well, in the definition of the previous algorithms, I was assuming that P and the number of processors and the size of the data equals the same. So the consequence of this is that if you have a number of steps, a number of elements that is exponential, 2 to the power t, then this model can do the sum in t steps, or it is the logarithm of n. Here is how this theorem is applied. So it has P processors. It's actually more general than that. So you can see that if you have sufficiently many processors, then this will be logarithmic in cost. So it allows us to derive the parallel time as the upper bound for the parallel time for this shared memory execution. Okay, so this ends this lecture, or actually I will state some references. So the theorem of Brent is a classical theorem dating from the 70s. I came across it when I was looking into the Encyclopedia of Parallel Computing, looking for the entry of barriers, which is under B. And then I found the article of John Gustafson. So it's a theoretical model. So we have actually already seen the very important law of Gustafson. He gives also an evaluation and a discussion of Brent's theorem that in the 80s it became actually clear that Brent's model was an oversimplification and not actually capable of providing an explanation for superlinear speedup. But nevertheless, it is a historical construction. The prefix sum algorithm is also a classical construction. It is available, it is described in this 1986 paper that guided the transition from serial to parallel thinking, and is also one of the archetypical constructions in data parallel algorithms, regardless of the architecture that you consider. So the references are more theoretical considerations, but still very useful as guiding principles in the design of parallel algorithms. So we've seen the definition of the butterfly barrier as a more efficient version of the tree barrier, which combined the fan in and the fan out broadcasts that we have seen earlier. So in some sense, we are advancing and kind of generalizing our knowledge, also our practical knowledge of MPI. So there is the send and receive. So MPI is very large, but we've seen already in the beginning that it does not take that many instructions and constructs to write really useful programs. The send and receive is quite useful to avoid deadlock, and especially if you have to implement your own butterfly barrier. So the exercises here are to experiment either with MPI or in C or with Python. We have not considered the full algorithms in full generality. So this is kind of the exercises that are left open here. Summation is an archetypical application that occurs with numerical integration, where one needs to sum ultimately a lot of function values. So you can see also a way of gradually approximating an integral. So in composite trapezoidal rules, we double the number of function values in each step. And in a way, this has the benefit that you can see that you have an automated error estimate, that you can see how much the approximations are improving. So in some sense, the prefix sum algorithm also serves as an algorithm that computes the differences between the different approximations. Okay, I hope this lecture was interesting. And in the next time we will see another application of synchronized computations, but now for the solving of large linear systems.